Okay, so let's do the introduction. So this is going to be the series number 1, and we're going to talk about the introduction for the robotics course. Okay? So, no, wait, okay, good. So we have some pretty pictures. All of them are very cool, but we don't want to talk about them. And everything is so cool. So the things really start to get interesting at here. So the definition of SLAM, okay? The definition of SLAM. SLAM is the abbreviation for simultaneous localization and mapping. So we will talk about that a little bit later, but let's talk about localization and mapping. So it's two different things. So localization means we know the map. We know all the stuff where they are, and we are trying to use the information that we observed and deduce where we are at. And we're using the vector sign that represents, we want to know it from time 0 to time t, okay? So this is localization. Okay. So this is localization. And for mapping, what is mapping? It means if I know my trajectory, I know exactly where I am, and based on the observation, can I deduce the map. And SLAM means we want to do the two things at the same time, because imagine that you have the street view vehicles that you basically have no idea what the map should be looking like. Then what it really is trying to do is we want to do the joint estimation of map and x based on our observations and our actions. So we will talk about what the observation and actions mean in a second. So I think this is a very cool video. This is a very cool image, right? Wait, can I copy it here? What the hell? Cannot do it? Oh my god. This is bad. This is bad stuff. No. Okay, so SLAM. If we want to talk about SLAM, we need to have some a little bit more information about what observation that we actually have. So imagine that there are many different landmarks on the map. So basically, you can imagine that you can sort of spot a few key points, like this is a lamp, this is a door, and then you can measure the relative distance and angle of the thing relative to yourself, your own coordinate system, and then this is your own vehicle. And then based on where your trajectory sort of is, and your estimation of the relative distance, which is the z, would also change. And you also have the information about how your acceleration would be, because you can use inertia measurement unit, which is abbreviated as AMU, GPS, and you also have all the throttle information. I think that includes the brakes and the gas and other stuff, right? So the point being, you sort of know how you can transition. So this is called actions. So you sort of know your transition from xt minus 1 and ut to xt. But you also can observe what is the relative distance of everything to you, right? So zi, you also have that. So slam basically means if we have observed this and this, then how can we estimate x and m conditional on the z 1 to t and u 1 to t, right? So full slam and online slam is basically trying to do the things for the whole trajectory or just one snapshot in time. So online slam means xtm 1 to t and u 1 to t. So I'm using all my history information, but I'm only getting the last frame. So that is called online. And the full slam means I'm doing that for my whole trajectory, which is just 1 to t, and everything is the same. Okay. So if you think about that, we know that A and B's joint probability distribution, if you sum it over all the possible scenarios of B, then you would get the marginal distribution of A. So if you think about that and let A to be xt and B to be x1 to t minus 1, then the full slam sum over all the state of 1 to t minus 1 would be the online slam. And this process is called marginalization. So I'm summing over the nonsense variable, which is the previous state. I don't care about what they are, but I'm just summing over all their possibilities and seeing, okay, through all the possible trajectories, what is the one, what is the sum of the probability that I'm stopping at here, right? So there are different trajectories over time, but I don't care about where they are. But for each one of them would have a distribution of the final xt, right? I sort of just convolve it. And then the convolution of that would give us the probability of xt over all the previous information, okay? Good. I think the next step, we would be trying to derive what is the Bayes filter. So let's look at that. Okay. So problem formulation. Our problem formulation is I have something given. Let's write Bayes filter here. So we were given an observation model. And we also have a motion model. So the motion model is just based on my action. Based on my action and my previous state, what is going to be my state without any correction, okay? So we were trying to find the goal of the belief, which is just a fancy name of a posterior. Okay? So, let's just sort of step back and try to solve the problem for ourselves. How would we tackle this problem? So first of all, if we want to solve this, intuitively, we want something that is a recursive relationship. So a recursive relation would be, well, xt is a function of, well, xt minus 1. And then if we somehow initialize the bell x naught, then we can do online update for all time steps, and then we can get the probability distribution at any given time t. So apparently we're going to use some Bayes rules for this problem. So let's see whether we can solve it on our own. Okay, so P So I think the first thing I would like to try is I would like to try to use the motion model, because it's very clear that it's trying to connect my previous state to my next state, right? So my bell xt minus 1 is simply pxt minus 1 conditional on u 1 to t minus 1. Let's just write till t minus 1 it's e till t minus 1. Okay? So a very simple thing we would always like to try first is xt and xt minus 1. What's the joint distribution? Still conditional on t minus 1. Let's just write t minus 1 here. So that would be pxt Well, this is just a belief of the previous time, right? So let's let's give them a new name. So we're calling them PBM, which is produced by motion model. And the next thing we want to do is we want to correct that on joint distribution. We want to marginalize it so that we can have a distribution that is exclusively about xt. So the simple thing we want to do is, so first of all, ut doesn't affect anything about xt minus 1 if not conditional on xt, right? So we can safely ignore that part of the correlation. So xt would be is just so this part is the motion model of t, right? So the motion model at time t times spell at t minus 1 sum over xt minus 1. Okay, good. So here we have something which is good, but what we really want is xt conditional on u to t and z to t, right? So what we want is to establish relationship between those two. So apparently we want to use something like a Bayes rule. So first of all, I feel like I'm not doing the right thing, but let's see. Right, this sort of feel like you just need z to t is what we have, right? Is what we have. So this thing over p of z. Right? So if we write it explicitly, so this is just m motion of t, belief of t minus 1, dxt minus 1, and what is p zt? So somehow we want to use our measurement model. So our measurement model, so PZT, so let's write it in a different way. So this is motion of t. So this is measurement of t, right? yeah, that sort of feel like just the thing we want to get. Now that we have it, let's see whether we're getting the right thing. The Bayes filter, I think it's in lecture note number 3, but it's totally fine if we are missing it. I think it's just a very interesting process that I really want to look at, whether I'm getting the right thing in the right way, and if something that's just bad, I really want to know where I got it wrong at the first time, and how would I think of it as the right way in the next time, right? Okay, so here is the Bayes filter, right? That's the thing. Yeah, to try to understand it, let's write it down. So from slides, the recursive relationship is Bell x of t is equal to, I guess, some normalization factor of p x z t x t times the prediction, which is, well, basically it's the motion model. So this is measurement model t, this is the motion model of time t times the Bell xt minus 1 dxt minus 1, right? So I think we were, what's really wrong about this is this should be one of the factors, but we have a 1 over x thing over here. So we will try to solve this puzzle next time, and stay tuned. Thank you.